On? Okay, good morning, ladies and gentlemen. So we talked about quantum mechanics, or we started talking about quantum mechanics last time. So first of all, again, if you have any questions right now, let me pause for a few minutes before I start discussing some of the perhaps weirder features of quantum mechanics. Hopefully you will have questions then. If you have any questions now, speak up. If not, the ideas we introduced last time is the fact that in physics, this is called duality. It's actually quite a popular concept in when it's applied to many concepts in physics. So the physics of the 20th century, as it turns out, has been primarily developed, the theoretical physics in the 20th century has been developed from the sort of point of view of symmetry and beauty in nature. As it turns out, these ideas that certain phenomena can be described by symmetries, by something that nature, for some reason, has chosen as a relatively elegant implementation of particular physics law. These ideas, as it turns out, have a lot of appeal now and have been proven in the 20th century's physics to be true or correct or applicable to many situations. This idea that both particles and waves, or both rather energy particles, photons, electromagnetic light, is a carrier of energy over space. Electrons can also carry energy, can carry kinetic energy, they have electric charge, and therefore they can experience potential energy as well. But electrons are particles of matter. They build up the elements in the periodic table together with the appropriate nuclei. They didn't, in theory, have to behave similar to particles of energy, like photons, but they do. And this idea that both sets of particles, so both carriers of energy, the matter and energy, can be described as simultaneously, under certain conditions, the particles of energy behave like waves. So electromagnetic waves, when the wavelength is long, behaves like waves. When the wavelength is short enough, we can describe them as particles, and vice versa. Particles of matter, like electrons and nuclei, can also, under certain conditions, behave like real discrete objects known as particles, or under certain conditions, they behave as waves. So this duality, the sort of dual role, the simultaneously dual role of particles and energy is quite appealing, and also the fact that you can describe both energy and matter in a similar way. So quantum mechanics as having both properties of matter and properties of waves, properties of particles and properties of waves. That idea that you can describe everything in the same language is quite appealing. This is one of those symmetry arguments. What's the way we describe matter now is that under certain conditions, if the equivalent wavelengths that we can assign to matter waves is large compared to the sizes of the objects, or put it the other way, if the sizes of the objects that interact with matter are small compared to the wavelengths of the wave we assign to the matter waves, then there's then the matter effects, the matter behavior, the wave behavior of matter becomes more apparent. So this was this idea by Louis de Broglie, this gentleman, I believe is Louis de Broglie, that we can associate the wavelengths with the particle that have a specific momentum. And the wavelength is inversely proportional to momentum with this coefficient here that's known as a Planck constant, a small enough number that the wavelengths you compute, or the wavelengths that is appropriate for matter waves is extremely short, of the order of nanometers or shorter, and therefore matter only starts behaving like waves, so at least that wave behavior is only apparent when we look at matter at very small distances and make it interact with very small objects. And so the smallest objects we know are in fact atoms in the periodic table or the atomic nuclei that are even smaller. The typical size of the atom is about an angstrom, that's 1/10 of the nanometer. And so that size is small compared to the wavelengths of matter waves that can be nanometer or shorter. And so in the early 20th century, when the physicists were faced with a conundrum, with a problem, there were actually two problems. One was called so-called the infrared death of the, or infrared problem, infrared death of the universe. Well, the other one was ultraviolet catastrophe, and the third one had to do with electromagnetic radiation. So, you know, clearly very dramatic names were assigned to these problems. The ultraviolet catastrophe was understood at the time as the problem with thermal radiation emitted by stars, or actually thermal radiation emitted by any warm object. As it turns out, if you do the very classical 19th century calculation about how much energy would a hot object emit, and what kind of spectrum would a hot object produce, if you do this according to 19th century physics, you would find out that actually the total power emitted by a hot object doesn't have this particular shape. In other words, per unit of wavelengths, the spectral energy would not rise, have a peak at some place, and then fall down, but it would continue rising indefinitely. And therefore, if you integrate that total spectral energy of all wavelengths, specifically over short, this side, right, spectrum would actually rise this way. If you integrate over very short wavelengths, you would get infinite energy. So in other words, from classical theory, one could predict that any hot object would emit infinite amount of radiation, most of it in ultraviolet and higher energies or shorter wavelengths, but still infinite amounts of energy. That clearly is inconsistent with observations. Right? We are warm, we emit radiation. I showed you infrared pictures of yourselves, but you don't emit infinite amount of energy. You emit finite amount of energy of about 1 kilowatt. If you emitted infinite amount of energy, then no matter how much you ate, right, all of your energy would be drained. Eventually, that's not good. So this problem, the fact that the spectrum observationally from warm bodies disagrees with the predictions of classical theory, was one of the things that motivated quantum physics, the description of quantum physics. The other observation was the fact that if you put an electron in a magnetic field or put an electron in an electric field and make it accelerate, make it experience forces, those electrons typically radiate. We use this fact to produce X-rays today. X-rays in an X-ray machine in a dental office are produced by accelerating electrons over some voltage of about 10 kilovolts or so, and then slamming them into a thin foil that stops those electrons very quickly, so it creates force and acceleration on electrons. Electrons stop, and while they stop, they emit so-called braking radiation, otherwise known as Bremsstrahlung, German name. It's basically a sort of similar effect as if you're driving in the car and slam on the brakes, you want to fall, forward. If you make electron do that, what follows forward is its energy, roughly speaking. So, this has been known since James Maxwell wrote his equations that accelerating objects emit electromagnetic radiation. But that's inconsistent with the concept that atomic atoms consist of a dense core of positive charge and electrons orbiting around that core, which have negative charge. Electrons have been observed in the early 19th century by actually even earlier by Thomson. The whole core of the nucleus was observed by Rutherford in his famous Rutherford scattering experiment. So in the early 19th century, this planetary model of atom started to take hold. The fact that atoms have a dense positive core and a cloud of electrons surrounding it, sort of similar to how a heavy sun is surrounded by orbiting planets. But that model had a problem in that, according to James Maxwell, if you make electron orbit a positive core, in order for electron to stay on the same trajectory, it has to experience a force similar to our planet being gravitationally attracted to the sun. That gravitational attraction is what keeps us on a constant trajectory and doesn't allow us to fly away into space towards Alpha Centauri somewhere. So the same thing has to happen, as we understand, in the atom. And then if you work out the Maxwell's equations, you would predict that if the same thing happens in the atom, the atoms would eventually lose energy, spiral down, and fall into the nucleus. And so in other words, this planetary model of the atom is unstable, according to classical physics. Luckily for us, Earth doesn't radiate that much. Earth, when it rotates around the sun, does not radiate. The radiation depends on the mass of the object, as it turns out. Plus, on average, Earth is not electrically charged. That helps too. So for electrons, on the other hand, electrons are very light. They would radiate a lot of energy and eventually spiral down in a very short period of time into the atom. And so the Rutherford observations of a core nucleus and a loose cloud of electrons was inconsistent with the fact that we know that molecules exist. We know that atoms exist, and we know that atoms exist for billions of years, at least. And yet, according to classical theory, they shouldn't exist. All the electrons should eventually fall into the nucleus. So this gentleman, at the turn of the 20th century, have decided to change the classical picture and invent a postulate. This was actually one of the few examples in the human history where the quite revolutionary idea, completely different from what physicists knew at that time, was postulated by theoretical physicists, which was postulated, the ideas were postulated to explain known phenomena, but also led to predictions which we now can observe. So the postulate's more that if you, again, postulate duality between matter and energy, that we know energy can behave as waves in the form of radio waves. If you postulate that matter can behave as waves under certain conditions, then we can say that there are configurations where electrons could form a standing wave around the nucleus. This is the Niels Bohr idea that in order for atoms to behave, to be stable, in order for electrons not to radiate, the atomic orbit, that wave that is created by electron as it moves around the nucleus has to be self-sustaining, has to kind of be self-reinforcing, and has to behave in a way similar to how the sound from a bell or the oscillations of campanile bell, of a circular circumference bell, works, where he postulated that if electron forms a standing wave on the orbit of the atom in such a way that exactly an integer number of wavelengths fits around the circumference of the orbit, in that, under those specific conditions, electrons do not radiate. It's a postulate. But this postulate has a testable consequences. Campanile bell tolls at specific frequencies, right? You can go out in 3 minutes. Don't go out in 3 minutes. You can listen carefully to the campanile bell in about 3 minutes, and it tolls at some specific frequency. You guys who have musical ears can tell me what that note is. It's I don't know, somewhere in the middle octave, it's probably 300 hertz or so. By listening to this bell, I can actually, and knowing what the speed of sound is in the brass, that's a few kilometers a second, I can actually tell you how big the Campanile bell is. This is one of the cute physics problems that we used to give to graduate students on the when they just entered Berkeley. We had this preliminary examination for graduate students. This is one of my favorite questions I would ask them on this exam. You know, what's the size of the Campanile bell? You've never been up on the tower, listen to the bell, figure out how big the thing is, and it's about this big. And you can figure it out by knowing what the note is, what the frequency of that note is, what the speed of sound is. Therefore, you can figure out what the wavelengths of the oscillation is. And that wavelength has to fit exactly integer number of times around the circumference of the bell. The wavelengths of the note in brass fits exactly in the circumference of the Campanile bell. You would predict the bell is about this big. The higher the frequency, the shorter the wavelengths, the smaller the bell. That you guys know, right? Little bells the Campanile has a big bell and a whole bunch of little bells. Little bells chime at higher frequency, higher pitch. The big bell is at lower frequency. So size is inversely proportional to pitch. Similar idea works for the atoms. The atoms with a very large orbits would have electrons with a relatively large wavelengths and therefore lower momentum and lower kinetic energy. And only specific frequencies could be heard from the Campanile bell. Only specific frequencies are excited by the bell, and in a similar way, only specific orbits can fit around the circumference of any particular atom, and therefore it can only emit only certain radiation is only certain frequencies. So this predicts this discrete picture. I'm not sure what happened to the fonts here. This discrete pattern of radiation that every atom emits. This becomes a testable, so this theory becomes very predictive and testable. We could identify each atom. The size of the orbit around the atom depends on the atomic charge, depends on number of electrons on the orbit. And so by knowing the charge of each nucleus in any periodic table, we could, at least theoretically, conceptually, compute the pattern of radiation each atom would emit. So each atom in the periodic table has this very specific fingerprint that can identify it. That has to do with its atomic structure, basically the sizes of orbits that can accommodate electrons. This is the pattern of radiation emitted by hydrogen spectrum. This is also, as it turns out, a pattern of radiation that the hydrogen atom can absorb. As it turns out, if electron sizes, the sizes of the orbits are fixed, and are fixed by the charge of the hydrogen nucleus, the atoms emit radiation only when they change orbits, when they transition from low orbit to high orbit, or the other way around. When the electron transitions from low orbit to the high orbit, it needs to absorb energy. When it transitions from high orbit to low orbit, it emits energy. And since orbits are fixed, the pattern of radiation absorbed or emitted by a particular atom is exactly the same as also fixed. Represents certain lines in the observed emission or absorption spectrum. And so, if you observe this pattern that tells us the energies in the atom are so-called quantized, fixed, have discrete patterns. Once we figure that pattern out, we can actually identify atoms by that pattern. So this becomes a tool in various forensic investigations, potentially. It becomes the tool for measuring how much of each particular element can exist in a sample. You can do something known as spectroscopy, observe the pattern of radiation emitted by a particular element or pattern of radiation absorbed by a particular element, can identify that element quite unambiguously. If you watch crime shows or NCIS, right? There's this woman, what's her name? Abby? It has this cool lab, tabletop experiments. She runs a few, pushes a few key buttons and can tell you, what the poison was or something like that. That can be done by either performing chemical analysis or more actually quite effectively by performing a spectroscopy analysis, by identifying radiation lines emitted by a particular atom. This is incidentally also how we know how much hydrogen exists in the universe. We actually counted. We know roughly 5% of the universe mass is in gaseous hydrogen that's spread out between the stars. About 0.5% of universe mass is actually in the stars, and another 4.5% is the helium gas that fills the empty space, not so empty space, between the stars. How do we know this? Well, we cannot, we haven't been to any other star. We know this by observing how light propagates from a distant star, like Alpha Centauri, the closest to us, or even further stars and galaxies, and seeing whether specific energy, specific wavelengths get absorbed. And if we see a pattern like this, if we see, for example, that, 100 nanometer radiation, the UV line isn't there. That means that the light emitted by some distant star gets absorbed for this particular frequency, for this particular wavelength. If we know this, and we know how much of the light gets absorbed, we can compute how much hydrogen was in the way. And that's one easy way, relatively easy way, to figure out how much matter is in the universe and what kind of matter. We can look at the distant star and actually look at the pattern of radiation emitted by that star. If we see the hydrogen lines, we will know that the star is full of hydrogen. Well, duh, that we know. But we can also figure out whether there are any other elements. How much helium, the older the stars, the more fuel, hydrogen fuel it burns, the more helium and heavy elements would be present. So we can measure something called the metallicity, which is identifying elements heavier than helium in the star by looking at the emission spectrum. So it becomes a very useful tool for fingerprinting, identifying molecules in various samples. And this is an example of using quantum physics, of application of quantum physics. This is the direct consequence of the fact that electrons form stable orbits, standing waves around atomic nuclei, and therefore only specific orbits are allowed. I have a little demonstration of that. Well, not of that, but another. This is one proof of the quantum theory, or at least of this duality between matter, particle properties of matter, and the wave properties of matter. But one can also make a more direct demonstration. If you remember, last time I showed you diffraction and interference patterns produced by laser beams. Lasers are, we'll discuss lasers a little later. Lasers emit light, electromagnetic radiation. And we know light behaves as waves. For example, when it's radio waves, so it stands the reason that light would behave like waves also for shorter wavelengths of visible light. So if we observe patterns that light produces in matter waves, in matter, that would be another evidence that matter under certain conditions can behave as waves. Now, in order for us to observe this, we need to send matter waves through some objects that have a size comparable to the wavelengths of a particular matter wave. So in other words, the sizes have to be on the order of nanometers. So we can send electrons through an arrangement of atoms. Atoms are always spaced roughly by the diameter of the atom. If the diameter of the atom is, let's say for the hydrogen, is about an angstrom, the matter waves with the wavelengths of the angstrom would behave like waves around those atoms. So here's an example of that. I have here a It basically is an X-ray tube, except without an X-ray producing target. It's a tube that produces electrons, accelerates them to, at this point, voltage of about 10 kilovolts. So electrons are accelerated in an electric field. Each of them have energy of about 10 kilovolts or so. And I can scatter them off of some target. Can we switch to the video, please? The target is actually carbon, not hydrogen. Well, carbon is more convenient. It's solid. I have a diamond film there and a piece of graphite. So diamonds in particular is most interesting. Diamonds form, what's the difference between diamonds and graphite? Graphite is what you write with. If you use pencils, it's a kind of loose arrangement of carbon atoms. It looks black or gray. As opposed to diamonds, which form a very rigid, organized structure, otherwise known as crystal lattice, where the atoms are arranged in a particular repeatable pattern. Atoms are always spaced by a fixed amount relative to each other and form a grid with very specific distances between each atom. So if I send electrons against that grid, electrons will scatter off, and radiation or scattering produced by each atom can either constructively or destructively interfere if electrons behave as waves. So in other words, the grid of the carbon atoms in the diamond behaves like a diffraction grating that we can use to spread out electromagnetic radiation or light. We can see patterns of constructive and destructive additions of the matter waves. And there it is. So I have an electron beam. So this bright spot in the middle is the primary image of the electron beam. The diamond, the piece of diamond, the diamond target that I'm scattering electrons off of is relatively thin. Most of the electrons just go through the middle. Some of them scatter, but they don't scatter at all possible angles. Electrons scattering at some specific angle reinforce each other. The scattering adds up coherently in phase and reinforces each other. In particular this, so you can see patterns of intensity that form concentric circles with fixed distances in between. This is very similar how electromagnetic radiation scatters off, again, a regular pattern, regular grid of perhaps dark and bright fringes on a diffraction grating. The electrons scattering at this angle reinforce each other, electrons scattering somewhere at some intermediate angle, the intensity cancels each other out. And so this is an example of wave interference, where, again, waves add up in phase, reinforce each other at this angle, and the intensities wash out at different angles. For diamond, which is very, I can increase the intensity, and perhaps you can see more than one ring. For diamond, well, okay, on my screen I can look at maybe 4 or 5 different concentric circles, 1, 2, and if you turn the lights off, you may see 3 and 4. This, oh yeah, there it is. You can see the brightest spot in the middle, 1, 2nd, 3rd, and maybe on this side you can see the 4th ring. This fixed pattern corresponds to a fixed pattern of atoms in the crystal lattice of the diamond. This is actually what makes diamonds transparent, makes diamonds also sparkle. This is a pattern that can measure the fixed distances between the carbon atoms. If I move the beam around a little bit, I can probably find a different pattern. This is actually a graphite target. So this is carbon. Oh, this is diamond. And let me turn intensity down a bit, and this is graphite. Graphite is a irregular arrangement of carbon atoms. And so you see scattering that fills out the space much more uniformly. Is the fact that the spacing between the graphite atoms isn't fixed completely. It's fixed only in one plane, but not throughout the volume. And so you get scattering at all angles is possible, and essentially an incoherent addition of intensity. The intensities that don't reinforce each other at some specific angles. Can we turn the lights on, please? So this is an example of a wave property of matter particles, electrons in this case, that's visible directly with an electron gun. I think I can turn this off. So again, matter behaves like waves when the spacing between the atoms is small compared to the wavelengths of the matter waves, and the matter behaves like particles when the wavelength is large compared to the other way around. When the wavelengths, when the object sizes are large compared to the wavelengths of radiation, of matter waves or of the energy waves, then those waves start behaving more like particles. And again, the sizes, so for example, for the atoms, the wavelengths of the radiation is of the same order as the typical size of the atom. And so the wavelengths of radiation can tell us about the sizes of objects that emit this radiation. So atoms typically radiate in the visible or ultraviolet range because the typical sizes of the atoms correspond to energies in the visible and ultraviolet range. If we reduce the sizes of the objects that emit radiation, then the radiation will be emitted at higher frequencies, higher energies, and shorter wavelengths. Wavelengths is comparable to the size of the object that emits this radiation. So, for example, nuclei emit gamma rays at the energies about 1 million times larger than the energies emitted by typical atoms. And this tells us that the typical size of the nucleus is about 1 million times smaller than the typical size of the atom. And that's about right. The size of the atom is about an angstrom. The size of the nucleus is, so angstrom is about 10 to the minus 10 meters, and the size of the nucleus is about 10 to the minus 15, so about 5 to 6 orders of magnitude smaller. All right, let me stop here for a second. The data is somewhat off by 2 days, but let me pause here for a quick check of how much of the chapter you've read. This is the quiz about lasers, which are devices like this, that emits highly collimated energy at specific color, specific wavelengths. And so we'll talk about operations of the lasers in a second. The question for you is what the main principle of the operation of the laser is: nuclear magnetic resonance, or NMR, fluorescence, quantization of charge, or a photon avalanche. I'll start my clicker, and you can dial in your answer in the next minute. And in the meantime, I'll turn the laser on here. We have a working model of the helium neon laser. It's this little bulb here, producing red coherent radiation. I'll give you about 30 seconds. Right, everybody, you guys done? Everybody? Let's look at the answers. Come on. Okay, so two responses receiving most of the votes, D as a photon avalanche and C is the quantization of charge. Let me show you how the lasers really work. The correct answer is D. Even though quantization of charge has a quantum name in it, that's not the main driving principle. Quantization of charge is the principle that actually says that elementary particles, electrons and protons, nuclei, have only specific values of electromagnetic charge. They are measured in the units of electron charge. So, any collection of electrons will have an integer number of electrons in it, and therefore the electric charge that's measured in the integer units relative to a single electron. And it turns out all of the elementary particles, including nuclei, and their constituents, protons, and even those constituents inside the protons and neutrons called quarks, have the values of electric charge that's a multiple of the charge of the electron. The reason for this is some fundamental symmetry in nature, but that particular fact is not significantly important for the laser operation. What's important for the laser operation is two effects. One is actual quantization, but the quantization of energy rather than electric charge. The way lasers work is by arranging a particular combination of atoms, typically a molecule of some kind that has at least 3 atomic levels in a particular range of energies. The reason for this actually is somewhat counterintuitive. As it turns out, hydrogen atoms, for example, single hydrogen atoms, do not laze very well. And the reason for this is that the radiation the hydrogen atom would emit is also the same wavelengths as the radiation that can be absorbed by the hydrogen atom. So if we have a single atom, typically, any radiation it would produce would be absorbed by any other atoms nearby of the same kind. And so lasers typically work by combining atoms of slightly different kind. This laser, for example, uses helium and neon. These are atoms in the last column of the periodic table that are so-called inert gases. And they have slightly different atomic properties, such as that the energy levels in the helium and neon are slightly misaligned between each other. And so one can have an arrangement in such a way that a particular energy from some energy source, usually in these gas lasers it would be a high-intensity lamp called flash lamp, which can produce radiation at multiple frequencies and many frequencies. The spectrum can be continuous like this. Certain frequencies of that radiation can be absorbed by the atomic system, and if electrons populate a molecule at one particular energy level called the ground state, those electrons can be excited by the pumping energy into higher-lying state, and then they will decay, emitting radiation. And so the arrangement is such as that there's an intermediate energy state where most of the electrons get stuck. This is called metastable state. The point of this third energy level is to create a configuration where most of the electrons sit at the energy level higher than their ground state, but they sit there for a long time. This ground state has typically relatively long lifetimes of microseconds to milliseconds. So if you're continuously pumping energy, this is sort of similar to creating a dam in the river. You can use pumps to pump the water up into the river, and you have a dam in the middle. Most of the water will be stuck above the dam. And then the next thing you want to do is open the floodgates and allow the stuck electrons to fall down to the ground state and emit the characteristic energy. In the laser, there's no atomic switch or atomic floodgate that we open. What happens in the laser is a single photon comes through, and that photon shakes the atom with a characteristic frequency that corresponds to this transition and shakes at least one electron off of its excited state into the ground state. That emits a secondary photon. So one photon comes in, shakes one atom, causes that atom to emit a photon with a very specific energy that corresponds to this particular transition. Now you have two photons. Those two photons can shake two atoms. Those two atoms will emit additional photons. And so each step in this process doubles the amount of photons in the system, which is exactly how the nuclear explosions work, and exactly the same how the avalanches work. Each consecutive photon will produce radiation from additional atoms, and the stream of photons produces an avalanche of energy that all have the same characteristic wavelengths that corresponds to this particular energy difference, and they're all collimated, that is, they all go in the same direction. The way the laser is typically built is there is an energy source known as a flash lamp. There's a lasing material that can be either a gas of some kind. Charles Townes, who's our Berkeley faculty, as a matter of fact, emeritus, has invented the laser in the 1960s by operating a gas of carbon dioxide that emits radiation at infrared energies of with the wavelengths of about 10 microns. This laser, as I said, is helium neon that emits red light with the wavelengths of about 640 nanometers. So the color that the laser emits depends on the atomic structure of the lasing material, depends on this difference in energy levels. And so you pick the material to produce radiation at specific wavelength, specific color. And then to improve efficiency of the laser, you want the photons that travel back and forth in this material and continuously shake the electrons off of the excited state orbits. You want to make those photons travel back and forth to this lasing material so that each photon can shake multiple number of atoms. And so there's typically a set of reflectors, mirrors, on the two sides of the cavity that contains the lasing material. So photons bounce back and forth. And one of these mirrors is partially transparent, so a small fraction of the energy is actually allowed to leak out. Photons typically make 10 to 100 bounces this way before they escape. So the transparency of the mirror is about 1 to 10%. So this is an example of a quantum mechanical device that uses the fact that energy levels in the lasing medium are fixed, and uses this technique known as pumping, or optical pumping, which literally behaves similar to pumping water above the dam and then, again, open the floodgates, except the floodgate here is a single spontaneously emitted photon. Now, of course, applications of lasers are numerous now in our daily life. We don't just use them to produce bright, shiny colors so that they can point to the screen. Lasers are characterized by three very convenient features. Most of the light is emitted at single wavelengths. So the produced light has nearly the same wavelengths. That's very useful if you're building devices that require wave-like additions of intensities, devices known as interferometers that can measure distances very precisely to a fraction of a wavelength of the visible light use this fact. The fact that the laser radiation is produced so-called coherently, that is, each photon oscillates in exactly the same way as every other photon in this laser beam, is also used in these devices called interferometers. But probably the most often used feature of lasers is the fact that the laser light is emitted in the same direction, in direction of the initially traveled photon, and the energy, and the lasers can produce a lot of visible energy. So energy is focused in the tiny beam spots, and a lot of energy can be delivered that way. So this fact is used in technology, for example, for focused laser energy can be used to perform eye surgery if you are using relatively low intensity laser beams. High intensity laser beams are used to cut metal, so-called laser torches, typically operate at infrared frequencies. The CO2 carbon dioxide laser invented by Towns is often used that way. Of course, lasers, the fact that the energy is very well collimated and the radiation has exactly the same wavelengths, can be used to observe small objects. And one of the small objects that we can measure with the high-intensity collimated coherent laser beam is a recording on a CD or DVD or Blu-ray disc that works by looking at reflection of the laser light off of the surface of the disk, and then the information can be encoded on the surface as a pattern of ridges and troughs, which would represent digits, zeros and ones. We can use also this fact, the fact that so for a CD disk, the intensity in the of the reflected light will be modulated, will depend on the pattern of the encoded on the reflective surface. So light may reflect strongly from the trough and less strongly from the ridge, as though if the distance between these troughs is comparable to the wavelengths of emitted light. Information can be encoded on the disk that way and then read out. And we can also use the similar encoding to transmit information over long distances. The fact that lasers are very well collimated and the energy doesn't spread out means that we can send information encoded in the laser beam over long distances, right? I can point a laser pointer over meters or sometimes kilometers and hundreds of kilometers. Single laser beam can be pointed at the moon, and if you have a sensitive enough photo detector, you might be able to see the reflection from the moon. We can send information over long distances encoded in the laser beams. I have a example here. Here's a neon laser whose power supply can be modulated by the output from a CD, or in this case, computer speaker, so that the intensity of emitted laser beam can be used to encode music, information, or sound. Here, the laser intensity will be modulated by the sound produced by the computer speaker. The laser intensity is detected by a solar cell, by a photodetector, and then played on an external speaker. James has particular taste in music. Of course, the efficiency of the transmission doesn't depend on a particular choice of music, but transmission still can be done effectively over large distances, independently of whether the carrying medium is empty space, or if the carrying medium is an optical fiber that can transmit laser light over long distances, but also can be made to bend around corners and deliver information into the households. So this is one of the applications of quantum physics, of course, lasers. The other application of quantum physics, as it turns out, is conversion of visible electromagnetic radiation into matter. This is known as photoelectric effect, and this, in fact, what makes you see. Photoelectric effect is another example of a quantum effect that works by converting electromagnetic radiation into charge carriers, electrons. So the way it works is that the light emitted by some optical source is quantized, that is, the energy carried by electromagnetic radiation is ultimately microscopically split into energy buckets of very specific energy, where the energy depends on the wavelengths. So if you go back to the concept of atomic orbits and the fact that the electromagnetic radiation emitted by a particular atom is quantized, is fixed in wavelengths, the same can be said about electromagnetic radiation that are absorbed by particular materials. Only specific wavelengths can be absorbed by this electromagnetic radiation. In particular, only very specific wavelengths can be used to absorb enough energy to kick an electron out of the atomic orbit. So for hydrogen, for example, you can, so this line at the 100 nanometers is the shortest wavelengths of radiation produced by the atom, or the shortest wavelengths of radiation absorbed by the atom. Any energy larger than this, with the wavelengths shorter than about 100 nanometers, will take an electron and not move it to a higher orbit in the hydrogen, but emit it, ejected from the atomic orbit. So any radiation in this range will be absorbed by the hydrogen atom, or radiation at these specific lines, will be absorbed by the hydrogen atom, but not eject an electron out of its orbit. Radiation with the wavelength shorter than that can eject electrons out of the orbit. So this photoelectric effect is highly sensitive to wavelengths of light. Short light with very short wavelengths can be absorbed by an atom and cause electrons to be ejected from the orbit. And wavelengths longer than that will not be able to eject electrons out of the orbit. And so if the energy is, if the radiation is energetic enough, then electrons can be produced, and then if you apply an electrical voltage near the surface where the electrons are ejected, electrical currents would flow through space. This is what happens in any photosensitive detectors. For example, in cameras, your digital cameras work based on this photoelectric effect, where visible photons eject electrons from the atomic orbits of silicon atom. Silicon sits here in the middle of the periodic table, is sensitive to visible light. It has the shortest wavelengths that can eject electrons from the silicon is in the visible light range with the energies or the wavelengths of sort of about a micron or so, somewhat less, about 700 nanometers or so. And so in the silicon devices, otherwise known as CCDs or charge-coupled devices, visible radiation emits electrons from the silicon, and then applied voltage will collect those electrons in the form of electrical current. And so your photocamera will sense the electrical current at a particular spot on the charge-coupled CCD device and register it as a digital bit in some digital file. Your human eye works also very similar, where the absorbed radiation knocks out electrons near or in the photocells in your eye, producing small electrical currents that are then send electrical signals to your brain. And similar devices can be used also to detect very low levels of radiation. So typically, if we want to detect relatively low levels of light, we use devices called photoelectric multiplier tubes, or PMTs. This is a device like this. It typically has the front face that's sensitive to visible light, that can absorb photons, electromagnetic radiation, at typically visible light energies, wavelengths of maybe 4 to 500 nanometers. Electrons are emitted from the surface of this cathode, from this metal. Typically, the metal is, the cathode is covered by material by the cesium atoms that has a relatively low, has a relatively good sensitivity to visible light, relatively low threshold for absorption of photons. And then those electrons can be accelerated in electric field in the photomultiplier tubes, producing a cascade of electrical current, which are then detected by some electronic devices. We'll probably show this demonstration next time. I brought this piece of equipment. This is a combination of photomultiplier tube, like this, connected to a crystal of sodium iodide. Sodium iodide, so here sodium in the periodic table, iodine is the heavier version of chlorine. So sodium iodide is basically heavy salt, or iodine salt, similar to sodium chloride, but a little bit heavier. This turns out to be a very good gamma ray detector. So in this device, single gamma rays with energies of mega electron volts can be absorbed by the crystal of sodium iodide, emit visible light detected by a photomultiplier tube, and then that energy can be converted into electrical signals and then ultimately converted into data. We'll try to demonstrate this or show how this device works to you next time. As it turns out, our high voltage supply didn't quite work with this device today. The nice feature of this device is that it can actually see single gamma quanta. So it can observe single gamma rays that can be produced either by radioactive atoms, and so this can be a radiation detector, or by other processes. So this is another example of technological application that uses the fact that electromagnetic or even electron energy is quantized, that is always split at the microscopic level into specific values of energy, specific energy buckets. So, we've so far talked about applications of quantum mechanics. Actually, the last thing that I wanted to show you, which we showed you before, is the operation of solar cells. Also works on this principle of photoelectric effect, where the electrons are ejected from the orbits of a particular atom. Well, in this case, I think this is a gallium arsenide semiconductor, again in the middle of the periodic table, that's also sensitive to visible light. And so operation of solar cells is actually quite sensitive to the spectrum of electromagnetic radiation. Visible light can produce a lot of electricity because photons of visible light have enough energy to kick electrons out of the atoms of gallium and arsenic, if this is gallium arsenide. At the same time, infrared radiation, so this is an infrared lamp that produces radiation of lower energies and longer wavelengths, isn't very effective. So you have to trust me on the fact that this flashlight actually works. It produces infrared radiation, but that energy is barely enough to produce electrical current. There's a small part of the spectrum that has high enough energy, most of the intensity isn't absorbed by this atom, by these atoms. Okay, so in addition to technological applications, quantum mechanics is often known by the conceptual puzzles or conundrums that may be difficult to understand or more difficult to accept even by the scientific community early on when the quantum mechanics was first introduced. Quantum mechanics was introduced to solve certain problems in classical physics at the turn of the 20th century, but the solutions were somewhat counterintuitive. And so it took a while for the scientific community to accept them, primarily through performing experiments that confirmed some of these features. Some of the features that you may have heard about are listed here. For example, the fact that no matter how good of a device you make, any quantum mechanical measurement will have an uncertainty. This is known as Heisenberg uncertainty principle. I'll tell it, I guess we can discuss that in a second. Probably the most controversial issues of quantum mechanics are randomness of any quantum process and the so-called superposition of states. The fact that certain quantum mechanical processes can appear to violate Einstein's principle of relativity that we'll discuss next time, the fact that the information can only be transferred over distance with the speed of light or slower. And so we'll chat about that in a second, and then the issues of tunneling. So let me first talk about the Heisenberg uncertainty principle. This is the actually relatively well understood phenomenon now. We've talked before about diffraction, about the fact that if you send a wave at an opening, this wave will spread out, which means the direction of the outgoing wave packets spreads out and becomes more uncertain. If you start with a wave that is very well collimated, the wave that always goes in the same direction, and impinge that wave, they have this wave penetrate through an opening whose wavelength is small whose size is small compared to the wavelengths of the wave will spread out, and its direction will be more uncertain as the wave propagates outwards. So this phenomenon is very well known for ocean waves. This phenomenon is very well known for optical waves. And the fact that matter also behaves as waves, except these are somehow probability waves, also means that matter waves can also experience diffraction. And one way to understand this diffraction is to say that if you imagine particles, if you imagine the wave coming at this opening from the left-hand side being particles, and you imagine the fact that the particles penetrate through that hole being a result of a measurement. Effectively, if you know that if a particle goes through the hole, it was at some point somewhere in this volume, the fact that this volume has a certain size and therefore the position of the particles that penetrates through this hole has an inherent uncertainty of this size, delta x, means that as the wave propagates outwards, exhibiting a diffraction pattern, the angle of the outgoing particles will be uncertain, will be spread out. And so Heisenberg realizes this. We now express this in terms of this uncertainty principle, which means that if you measure something with a very small position uncertainty, very small hole, the outgoing direction or the change in momentum, the momentum of outgoing particle will be highly uncertain. This is how diffraction works. The smaller you make this hole, the larger the spread of the outgoing wave would be. And so if we measure something extremely precisely by making the hole small, the outgoing direction or momentum will be highly uncertain. Or the other way around. If you want to measure a particle with a very small uncertainty in momentum, uncertainty in its position would be very large. We will need to make a hole of a very large size. So this is the inherent property of matter and electromagnetic waves, the fact that one cannot simultaneously measure direction and position with absolute certainty. If you measure position of something absolutely precisely, its direction, angle will be absolutely uncertain. You'll have very large error. If you measure angle very precisely, the position would be very uncertain. Those uncertainties, the product of those uncertainties cannot be smaller than some constant known as the Planck constant h. The same as it turns out to be true for time. If you trying to measure some energy of some particle extremely precisely, you have to know when a particular process happened with a large uncertainty. That also means you have to observe that particle for a very long time. And vice versa. If you want to measure at what point the particle passed through your detector, the energy of that particle will have a corresponding uncertainty. And the product of the two cannot be smaller than some well-defined, small but a well-defined number. This is basically application of diffraction wave principle to matter waves. Randomness, well, randomness is this inherent feature of quantum mechanics. I said before that we describe matter as so-called probability waves. So in other words, we can describe propagation of particles in terms of, or we can describe outcomes of experiments in terms of probabilities. We cannot predict with absolute certainty an outcome of any given measurement, but we can compute probabilities for some outcome to happen. This is sort of similar to playing a lottery. If you know that million people have bought million tickets and you bought one, you can predict if the result of the lottery is not rigged, that you have 1 in a million chance of winning a jackpot, but you cannot, before you do the measurement, predict with absolute certainty whether you will or will not win the jackpot. As it turns out, nature works at microscopic level in exactly the same way. You can predict what a range of outcomes is possible. For example, as I said, dropping this piece of chalk on the table, I can predict several possible outcomes: the chalk stopping at the table, the chalk scattering off of the table, the chalk tunneling through the table. Based on the forces that are involved in this particular experiment, I can predict chances, probabilities, for example, for the chalk tunneling through the table, but I cannot predict with absolute certainty every particular outcome. This was highly controversial in early 20th century. Einstein, so this quote that God doesn't play dice is attributed to Einstein, who was very unsatisfied with the fact that we cannot with absolute certainty predict an outcome of a physics experiment. This is opposite to the original idea of quantum physics, of classical physics rather, that if you measure all of the forces, then you can predict the trajectory of all of the objects. Quantum mechanics doesn't work that way. We can predict odds, but we cannot predict certain outcomes, or we can predict outcomes with certainty. Another one is the superposition of states, so spooky action is in the distance, often attributed to Edwin Schrödinger, of the Schrödinger cat fame. The story goes as follows. So, the fact that quantum mechanics predicts only probabilities, but rather than certain outcomes, leads to this particular thought experiment. So imagine that you put a cat in a box. This is a thought or so-called Gedanken experiment, and no documented experiments with real-life cats were performed that way, I hope. So imagine the situation where you put a cat in a box, you add to the same box a vial with poisonous gas, and a little device that will open the vial if some quantum mechanical process happens. Say you put a photomultiplier tube next to the vial, you connect the electrical signals from the photomultiplier tube to the gate that opens the vial, and you make the gate open if, let's say, a uranium nucleus decays nearby. produces a gamma ray that is detected by a photomultiplier tube that opens the gate that emits the poisonous gas that kills the cat. So if you close the box and try to predict what will happen to the cat, there are two possible outcomes. A particular quantum mechanical process can happen. For example, the uranium nucleus, it sits there, and we cannot predict with absolute certainty when this uranium nucleus will decay. It will decay at some point between now and a billion years from now. We cannot predict with absolute certainty when that happens. So if we wait less than a billion years, then we'll know that if we, over the lifetime of the cat, that's shorter than a billion years, the vial will either be open or it will not. Quantum mechanically, we describe this cat as a superposition of two possible states, dead cat and a live cat. So as long as the cat is in a closed box and we don't have any information about what's going on inside, we view the system as a superposition of two possible states, and they can quantum mechanically interfere. Over time, they all behave as probability waves. When we actually open the box, we perform a measurement. We open the box and we actually look at the results. That's an experimental application. That's an act of an experiment. Each experiment can actually affect the outcome of the state of the system. It's known as collapse of the possible wave function. It identifies a state as either dead or alive. Until that measurement is done, the cat lives in a superposition of a dead cat and a live cat state. Opening the box is equivalent to collapsing that state into one or the other. So we can predict probability that as a function of time that the cat is dead or alive. We cannot predict with absolute certainty what happens when we open one particular box. If you have 1 million cats, then you can predict what the odds are over, let's say, the next year that each cat would be alive, and then by opening 1 million boxes, we can compute what fraction of the cats are dead and what fractions of the cats are alive, and compare it to our predictions. This is exactly how most of the quantum mechanical measurements work, in that we can compute the odds of various processes. So by performing experiment multiple times, we can confirm those odds. But in one particular measurement for one particular cat, the prediction with absolute certainty of what is happening is impossible. Let's see, what are the other puzzles? Well, tunneling is an interesting phenomenon. Also a quantum mechanical phenomenon. What it physically means is that a process that's not completely forbidden in quantum mechanics will eventually happen. That's sort of a colloquial way of expressing the phenomenon of the tunneling. Also, it expresses the probabilistic nature of quantum mechanics. The fact is that if some process is not strictly forbidden, means that the process that's not strictly forbidden has a non-zero probability of happening. If probability is not zero, that process will happen eventually. If you repeat the experiment enough times, eventually you observe every possible outcome of the experiment, no matter how unlikely the outcome is. And so in particular, the probability that a chalk somehow penetrates through the table, kind of squeezes itself between the atoms in this piece of wood is highly unlikely. Probability is extremely small. But if I repeat this process enough times and be persistent enough, eventually it will happen. You guys don't have to wait. Of course, the probabilities depends on the sizes of my piece of chalk. If the size of the chalk is small compared to the distance between the atoms, well, then this chalk will just slide through like knives through butter, or like the Rutherford's helium nucleus can slide through the arrangement of copper or gold rather nuclei in a gold foil. So really the probability for this process depends on what kind of physics is going on when the chalk interacts with the table. If the chalk size is small, wave effects become important, then this tunneling becomes more likely. In particular, tunneling usually refers to a situation where you have a, well, what's the best situation to describe this? This depends on the situation where you have a energy. I can plot energy of particular system. When the energy has a shape that sort of looks like a wall of a cup of a finite size. An example would be this. Somebody left this cup, I hope, less than a week ago. It's just water. So water sitting in this cup, filled up to a certain level, generally, classically, will sit in this cup forever until it evaporates. If the water surface is below the top surface of the water, the energy that's required to lift the water out is positive. And so in other words, the amount of energy in the water is lower, the amount of energy that's required to pull the water out of the cup, and the water will sit in this cup forever. This is the classical picture. Quantum mechanical picture says that as long as the size of this cup, the height of the wall of this cup is small, you can have fluctuations in the energy level of the water. And every once in a while, with some small probability, water can actually spill out and propagate outwards. And that, in fact, is related to this Heisenberg uncertainty principle, the fact that the energy of any system is not actually fixed, but rather uncertain. And so, effectively, the fluctuations in the water level, small fluctuations in the water level, means that every once in a while, some molecule can penetrate out and tunnel out of the cup. And if you give the system time, eventually all of the water molecules will, in fact, tunnel through the wall of the cup and escape. This is exactly how nuclei decay. Any unstable nucleus actually looks like water in this cup, where the protons and neutrons in the nucleus are represented by the water level, and eventually, over time, all of the neutrons leak out, representing the decay of the nucleus. This is the phenomenon known as tunneling. Just before I quit, we have a classical demonstration of this tunneling phenomenon. I have these two blocks of paraffin that can represent the two sides of the cup, and I can show that the microwaves can penetrate through the block of paraffin with relatively high intensity when the two blocks of paraffin are connected together. But even if I separate them, the electromagnetic wave still can penetrate through the gap, jump through the paraffin, and then propagate into the speaker of the radio receiver. So this is a phenomenon that's very similar to the phenomenon of quantum objects like protons and neutrons penetrating through the boundaries of the nucleus, and that, in effect, known as tunneling. So let me stop here. Next week, so I'll bring you a demonstration of photoelectric effect once more, hopefully when we get our high voltage supply to work, and we'll talk about other strange phenomena known as special theory of relativity developed by Einstein also at the turn of the 20th century. You guys have a good weekend.